Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, Managing the Lifecycle of Independent Protection Layers. Our speaker is Patrick Fisher. Patrick Fisher is a functional safety engineer at Provenance Consulting with experience in the industrial and refining industries with proven results in process hazard analysis, layer of protection analysis, facilitation and training, safety instrumented function design, and IPL management. As a PHA facilitator, he helps companies meet the PHA, MOC, PSSR, and PSI requirements of the OSHA PSM standard and help manages the results of the PHA LOPA results. His background includes publications on risk analysis, independent protection layer management, and leading indicators of process safety. One quick note before I turn the session over to Patrick Fisher. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Patrick Fisher. Hello, Patrick.
Hi, thanks, Pam, and thank all of you for joining us today as we're going to be talking about managing the life cycle of independent protection layers, or IPLs. Hopefully, if you're joining us today, you either work with IPLs or have an interest in working with IPLs. But maybe you're here just trying to find out, what's this IPL thing I keep hearing about? No worries, we're going to cover all levels of that today. See, IPLs are still a relatively new concept in petrochemicals and the general process safety industry. And even companies that have been working with these IPLs for 20 years or more are only just now discovering how complicated managing these independent protection layers can really be. At the same time, industry is also learning just how good IPLs are at managing and minimizing risk in these big facilities. To begin this conversation about IPLs, I could go back to when they first showed up around 1993 or what their origins are, but I'm not going to because, like so many safety concepts, IPLs didn't really become prominent in industry until a few things went horribly wrong. Horribly wrong happened in 2005. Two major incidents rocked the petrochemical industry. One was in Hemel Hempstead, UK, just outside London, known as the Buncefield Fire. The other was in Texas City, Texas, just outside of Houston. It's good to look at both of these events because they've been heavily analyzed by both government and industry groups based on the severity and the potential severity and how much they could have impacted the communities around them. Out of these investigations, it became very clear that there were striking similarities between the two events, including issues of poor safety culture, problems related to corporate cost cutting, and most importantly for today, both incidents showed a failure to manage the safety systems which the facilities relied upon. Out of these incidents, especially the Texas City incident, we saw an industry push to layer of protection analysis, or LOPA, and with that, independent protection layers, or IPLs. But that was only the start, because since then, we've learned a lot more about what's actually required in order to use independent protection layers to reduce our risk. That brings us to today, when we're going to be talking about what an IPL is and where it comes from, as well as what actually makes a good independent protection layer. Then we're going to move on to the life cycle of IPLs, looking at what needs to be documented and managed throughout the life cycle from start to finish on these independent protection layers. Finally, we're going to look at some industry practices that are being used today to manage these IPLs all the way through. To start with, I'm going to talk about what is an IPL. So to do so, we could go to many sources, including the IEC 61511 or S84 standard, which dominates modern instrumented safety requirements. However, I actually want to talk more about IPLs that are not safety instrumented functions, so the ones that the 61511 standard doesn't talk about a lot. So for that, I'm going to go to two books from the Center for Chemical Process Safety that do a great job about talking about these IPLs. The first, from 2001, codified LOPA as it's done in North America. I call this the purple book based on its cover. The other, referred to as the blue book, from just last year has taken everything we've learned in the last 15 years and used those learnings to make some much-needed additions, adjustments, and clarifications. One such clarification is actually the definition of IPL, which is an interesting change that I'm going to be talking about a fair bit today. Both definitions start the same, saying that an IPL is a device, system, or action that's capable of preventing a scenario from proceeding to its undesired consequence. Then they deviate a bit. The 2001 Purple Book says that the IPL needs to be completely independent of the initiating event or the action of any other IPL. The Blue Book makes a much-needed change here, dropping the word independent and saying that the IPLs cannot be adversely affected by an initiating event or action of any other protection layer. It's an important distinction that comes into the lifecycle management we'll be talking about later, and we will talk about what the difference is in a few slides here. On top of that, the Purple Book included in their definition that the effectiveness and independence of an IPL must be auditable. The Blue Book dropped this. I think that's mostly because it just doesn't make a lot of sense to have in the definition of IPL, since auditability is a property of the independence and effectiveness rather than a property of the IPL itself. Again, we will talk about that a little bit more in a bit. So what does this all mean for IPLs? Well, I'm actually going to stop talking about IPLs for a second and start talking about safeguards. So safeguards come from our risk analysis, which is looking at scenarios where an initiating cause, such as a valve failure or really any equipment failure, starts a chain of events that leads to a release of energy and ultimately a consequence to personnel or the environment or to financial impacts. Safeguards are anything that interrupts this chain of events, leading to a reduced likelihood of the consequence occurring. So this can be everything from your alarms, any operator actions, relief valves, and trips. There are a lot of these safeguards that we've identified, and just identifying them and guessing at the risk reduction from them works pretty well from the 70s and through the 80s and even into the 90s when we were doing these HAZOPs and using risk matrices. But as the later 90s came around and early 2000s, we wanted to start trying to actually quantify the risk reduction without going all the way to a quantitative risk assessment. So to do so, the concept of LOPA, or layer of protection analysis, was introduced, and that brought IPLs. IPLs are just special safeguards that we've taken as the important ones that we can easily quantify the overall risk reduction, and we can estimate how much the likelihood is reduced overall. So what is an IPL? An IPL is just a safeguard. And the statement I'm going to make, I'm sure a lot of you will disagree with at first glance, but I'm going to back it up. Any safeguard that we identify in the HAZOP can potentially qualify as an IPL if we can prove that it is independent, effective, and auditable. Those are the three criteria for identifying safeguards that can qualify as an IPL. And really, that's just a property of whatever we're looking at in terms of safeguards. Important to note here is I said that we pick only a few safeguards to turn into IPLs. Well, all of the other protection that we have in our facility is still really important. The Blue Book talks about how even safeguards that don't meet the requirements of an IPL are still important for overall risk reduction and good engineering practice. You should not rely on only IPLs for the protection in your facility. Safeguards are important, and you should manage those as well. So coming back to these three criteria of these special safeguards, the IPLs, let's look at the independence. What does independence mean? Well, if you remember from just a couple minutes ago, independence was something that actually changed in the definition between the two books. The Purple Book said that an IPL needs to be completely independent of the initiating event or the action of any other IPL. And the Blue Book went on to change that. They got rid of the word independent, actually, and said, without being adversely affected by the initiating event or any other IPL. Now, there's good reason for that. If we want true independence between our IPLs and our initiating events, there can be nothing that can cause a common mode of failure. But if we look at something like a pressure control valve going closed because the instrument plugged, and our protection is a relief valve, there's a certain potential that plugging of the instrument could also plug up the relief valve. The same thing for something where we're looking at a tube leak in an exchanger, and the operator action is to close a valve or open a valve. Both of these, or that has in common with the mechanical integrity programs. We actually have an entire program that's common and could be a fault. However, these cases are very, very low probability, to the point where most of us wouldn't even consider them credible. However, if we're truly saying independent, that's not a possibility. So the Blue Book talks about this, saying that the IPLs need to be sufficiently independent such that the degree of interdependence is not statistically significant, and that's an important phrase. We're saying that basically the chances of the common mode of failure are so low we can ignore them. And that brings it in line with standards like 61511 that speaks in a very similar way. So if we look at a safeguard from the HAZOP, we can say that it's considered independent if it has a non-significant interdependence with the initiating event, with the other IPLs, but it also has to be not adversely affected by the initiating event and not adversely affected by the other IPLs. So in this case, a lot of it comes down to calculating, are we low enough of a common mode of failure that these can be considered independent? So that's talking about a HAZOP safeguard and determining independence. The next criteria we want to talk about is effective. And effectiveness is about capability in the face of a challenge. You know, the Ghostbusters didn't try to fit all their gear in the back of a Pontiac Trans Am, as cool as that would have been. They needed a vehicle capable of holding all of their gear. In case of IPLs, we can actually look at the definition, and this was common between the two books, saying that the IPL needs to be capable, there we go, of preventing a scenario from proceeding to the undesired consequence. Now that's perhaps the most obvious case. We need our IPLs to actually work. So what does that mean? Well, for relief valves, that largely means we are doing the work that we normally need to do. Relief valve size for the scenario, set at the right pressure, you have the right service, so it's not going to plug if you want it in clean service, and it's regularly tested or replaced. An alarm, on the other hand, can in some ways be a lot harder to determine effectiveness. First of all, it obviously needs to be able to detect the scenario, but you need to make sure that there is sufficient time to act on the alarm. That's a reliable instrument, and perhaps the biggest one here, the operator action when they get that alarm, needs to be clear so they know exactly what they're going to do in order for it to be effective. So a HAZOP safeguard can be considered effective if it's functional to prevent the scenario without outside interference, it's got sufficient integrity for the risk reduction or probability of failure on demand, and it's reliable to provide sufficient risk reduction between tests. So between times when you actually go out there and try it, you need to make sure that you need to be able to rely on it to work. So that's independence and effectiveness. Next we have auditability, and remember that this also changed slightly in the definitions. Really what we're trying to say here is those previous two criteria, you need to somehow be able to test to make sure you're meeting those requirements. So on a relief valve, again, it's pretty easy. You need to be able to ensure it can be tested on a regular basis, checked for the service. But alarms can be a little harder. You need to test them on a regular basis from instrument all the way through operator action. You need to have documented what is the intended operator response so that when you record the actual operator responses, you can compare the actual response to the intended response so that you can really test that entire alarm with operator action. So these are the criteria, 3 criteria we need for identifying independent protection layers. What does that mean for our safeguards? So here I've identified a number of safeguards in the HAZOP that we would normally use. Alarms with operator action, trips, relief valves, procedures, post-release, operator rounds, etc. And I've categorized how easy it is to actually identify the independence, effectiveness, and auditability of each of these safeguards. And what we get is a few of them are really easy to do all 3. That's alarms, trips, relief valves. So these are going to make up, because they're so easy, they're going to make up about 95% of the protection in your layer protection analysis. And that's purely because they're really easy to determine these things. After that, we have things like procedures or post-release. These get a little bit harder, but are still relatively easy to verify the 3 criteria. So we use them less often, but we still use them. These are going to make up 4 to 5% of your protection in your layer protection analysis. Finally, we have everything else. These are hard to verify, but rarely are they impossible to verify. But basically, we don't really want to use these because it's a whole lot more work for us. This is where you might see your procedures say, you shall not use these as IPLs. It's because we don't want to do the large amount of work that's required to actually manage those IPLs. So back to what is an IPL? Well, an IPL is just a safeguard that we choose to focus our attention on because it's easier to quantify, qualify, and verify the safety protection provided through the independence, effectiveness, and auditability. So that's why you're going to get most of your protection from these 5 IPLs or similar. So back to my original statement that I said some of you may disagree with, that any safeguard identified in the HAZOP can potentially qualify as an IPL. Well, it can, but we're going to choose the ones that are easy to identify with those 3 criteria because we don't want to do more work than we have to. So that's all about identifying IPLs, which is really only the first step. The thing with IPLs is we need to manage them through a life cycle. And that means starting out with the documentation of the risk assessment that we're doing pretty well, along with analyzing the independence, effectiveness, and auditability. But we also need to make sure that we document all of that information basically ahead of time so that we can make sure that it's implemented correctly. So we're going to have to implement it independently and make sure we implement our testing plan so that we meet all of the requirements we said back in the identify stage. Finally, we need to make sure that we manage the change in modifying it. We want to make sure that any modifications we make do not affect the independence, effectiveness, or auditability of our IPLs. So how do we actually do this life cycle? Well, for that, I'm going to turn to first the blue CCPS book that we've already talked about, but there's also an additional green one on safe and reliable instrumented protective systems. And it talks about 7 core attributes of an IPL that need to be managed throughout the life cycle. Now, we just went from 3 to 7, which seems a little funny, but really it includes all of the same criteria we had for identifying the IPLs, the independence, effectiveness, and auditability, and then splits them out a little bit and adds on a few that talk about our entire systems for managing the IPLs. So let's look at these. The independence. This one, of course, is common with the initial criteria. To manage the life cycle of the independence, the biggest thing here is we need to identify all associated equipment, personnel, and control systems to make sure that there's not an issue with interdependence. We have to do that not just for the IPL, but also for any initiating events. We have to look at the potential failures that can occur, including, again, the equipment and personnel. If there's any element shared between the IPL, the initiating events, or other IPLs, we need to ensure that the probability of the common failure is less than the required combined PFD of the IPL and cause or multiple IPLs. So a good rule of thumb for this is our common mode of failure needs to be at least 1 order of magnitude lower than the PFD we want to take for our IPL. That's going to work for most cases. There are a few edge cases you have to catch. So that's independence. Now, effectiveness has been split into three here: functionality, integrity, and reliability. Let's first talk about functionality. Those of you who work with safety instrumented functions will recognize the phrase functional requirements, which is everything that's actually required in order for that IPL to work. So we have the instrument, what the set point is, what logic solver, final element, times, and the expected results. And we're going to try as much as possible to put this into phrasing that most people can understand. It's pretty simple. As an example here, we have an instrument, high pressure alarm, say what it's set at. It alarms through where the control system and the board operator needs to respond within a set amount of time, and we're going to put out what does he actually have to do by closing the fuel gas valve, and why to prevent the pressure from reaching the MAWP of 120 psi. This is, in plain words, the who, what, when, where, why of this IPL. We're going to want to put that out and say exactly what we need. Next section on effectiveness is integrity. Integrity is the what we can rely on this IPL to actually prevent. So this here is going to be your probability of failure on demand. So for every cause-consequence pair that we identified in the risk assessment, we're going to document what we required the PFD, probability of failure on demand, to be. And remember that that can be different. One IPL can have multiple PFDs depending on what the cause-consequence pair is. Important thing here is integrity is always limited to the weakest element. So how do we determine that? We're going to go back to that list we created in the independence stage and look at what the least reliable element is and make sure that the PFD is the same or lower than the total system of the IPL. So for example, a relief valve that is being used in a reverse flow scenario and relies on a check valve to limit the amount of flow that the relief valve is going to see, we can only get the probability of failure and demand of the check valve in that case, which would be a 0.1 versus the 0.01 that we usually get for a relief valve. And there's a lot more information about this in the blue book. The next section of effectiveness is the reliability. This is how often can we actually rely on this IPL. And what we're going to do there is we're going to document the design conditions that we expect that we're using to determine what PFD we can get, and document those, and then also include a plan for what to do if the IPL is not available. Maybe it's bypassed, maybe the instrument's not working, maybe something's going on operability that we can't trust it. We're going to want to make a plan ahead of time to say, here's what we can do in place. On top of that, we're going to track over time when the IPL is available and when the mitigation plan was available as well, and use that to determine did this IPL actually meet the reliability that we defined in the LOPA. So we're going to actually track the times the IPL was not available, and then 5 years from now we're going to say, was it available at least 90% of the time? Yes, then we can probably use, I should say, a 0.1 PFD for that. So those three make up effectiveness. Then we go into auditability, which is really just a property of those first four. We're going to plan ahead by preparing an audit plan that says how and when we're going to verify independence, functionality, integrity, and reliability of this IPL. At a bare minimum, the independence and effectiveness need to be reviewed with the PHA cycle, otherwise you're not doing your LOPAs. Important here is that each IPL should have a testing plan that includes all elements of the IPL. So that includes the instrument, your logic blocks, your control system, and even the operator action, right from them getting the alarm and responding to the alarm in a correct amount of time and taking the action that they need. The last two criteria are not necessarily criteria of individual IPLs, but they are a system-wide issue, so access, security, and management of change. Access security is saying that there need to be physical or administrative controls to reduce unauthorized system changes. This can be everything from accidental damage, where your MOC system fails and someone makes a change to an alarm set point, not realizing that it is that it's an IPL. Or this could even be a malicious change, where you either have a virus that changes your IPLs, or a disgruntled employee that makes changes that impact the safety. So we need to make sure that we identify these controls that are in place and document them so that they can be audited. Back to number 5 there, we need to be checking these as well. The last criteria the CCPS talks about is management of change. This is, to a certain extent, the easiest and to a certain extent the hardest part of this IPL life cycle. I say the easiest because we're actually pretty good at management of change at this point. It's been 40 years, and as much as there's been some issues, most people are at least familiar with management of change. The hard part is just how intricate the IPLs are when it comes to management of change. And that's saying that if any element of the IPL changes, or if any element of the initiating events change, we're going to need to make sure that we look at the whole system to make sure that we have not affected the independence or effectiveness of that protection layer and the initiating events. So there's a lot of work there. There's a lot more fine details in management of change for IPLs than there are for most management of change that we do. So when we go back to what comes after identifying the IPLs, well, the CCPS put together these 7 attributes which we're going to need to document and actually manage through the life cycle in order to make sure that our IPLs are going to work. The question comes, how do we actually do that? Even how do we document that? Well, there's a lot of different ways. I'm going to talk about one here, which is the documentation of individual IPLs. It's called the IPL Lifecycle Requirements document. Again, those of you who have done safety instrumented functions will find this familiar. It's very similar to a safety requirement specification, where we are defining everything that goes on in the life cycle of this IPL. Now, I'm going to go through the individual parts of this document. However, if you would like a copy of this, at the end of the presentation there will be 2 emails. You can email and we will give you a copy of this example document. So to start out with talking about the IPLs, let's talk about the information that goes into just the IPL, the top section of this Lifecycle Requirements document. Start with the description, which you'll recognize as our functional requirements in simple terms that we said before. This is all the same information, who it's important to, what sort of timing you have, and what you're protecting against. The next section, we're going to talk about where are we actually getting this from. So in this case, they identified this IPL in a HAZOP and LOPA revalidation, and we even point to the particular nodes. If that's an electronic document, obviously we would have a link to get more information about this IPL. You need that so that you can get more information if needed. The next section is going to talk about what elements make up the IPL. So here we're going to break it down into components. And this example here is down to a really fine level because we want to make sure that we don't have any issues with independence. We're going to include our instrumentation, so in this case just one instrument. We're going to include everything related to the control system, from input-output cards, CPU, logic blocks, even the screens that the operator is going to be looking at, because we want to make sure there's no issues with interdependence. We're also going to talk about the final elements, which in this case is an automated valve that the operator needs to activate. This could be a manual valve that they need to go close. Whatever we say there for the final element is what we'd list here. Finally, we're going to list all of the personnel involved in this IPL and the maintenance of this IPL. So who actually needs to act here? We have the board operator, but also someone who could impact the reliability of this IPL is the instrument tech out there doing the work. So we're going to list them and make sure that there's nothing in common between this IPL and our other IPLs. Next, we're going to list some information on the identified hazards. So we want to make sure that we know effectiveness and integrity here. We're going to take our PHA consequences, which document what we're protecting against. We're going to say what the risk is, along with what the probability of failure on demand expected for that scenario is. In this case, 0.1 for this particular IPL. Again, that can be different depending on the scenario. In this case, it's not. Next section we're going to talk about is the process safety time. So again, safety and function people will be familiar with this. The process safety time is the time between your initiating event and the release. However, for an IPL, it's often more useful to say how long do you have to actually act within this IPL. So I put in here the time from detection to release. So when the alarm goes off, how long do we have before a release could occur? And then we're going to want to list the expected time to action. So how long do we actually have to act on this IPL? In this case, 8 minutes. We want that to be around half the time at a minimum. Next, we're going to list the expected result. So this is what do we want to see this IPL actually do to bring the system to a safe state? Drop the temperature, drop the pressure. This is good for two reasons. One, the operator knows that the IPL is working if they see this result. Two, we're able to test that expected result over time as part of our auditability. One thing you may want to include in here that I don't have is process lag time, which is how long you have between the action and when you actually see the result. You could easily put that in this section as well. Next, we're going to look at the independence of the protection layer from both the initiating event and the related IPLs. So here we have a control valve malfunction closed. This is the initiating cause or initiating event, and we're going to list, just like we did for the IPL, all of the components: instrumentation, control system, mechanical elements, even the personnel. And what we want to do here is flag anything that's common between the two, which is a lot easier to do when you actually break it down to this kind of level. So we can see here highlighted that the CPU and the Area B board operator are in common. Now we're going to want to document why that is acceptable. So why is that degree of interdependence not statistically significant? So for the CPU, we've determined that the frequency of failure there is 0.01, so it's better than 1 order of magnitude from the PFD that we need, so we can say that that's statistically insignificant. On top of that, the board operator is common. However, again, we're in a low-stress, non-fatigued situation, so that is acceptable for this condition. We just want to flag it and say we looked at it at this point. We're also going to look at all other initiating events that this IPL is used for. So in this case, a manual block valve, where we're not particularly concerned about instrumentation in common, but maybe there could be some personnel in common, and we want to make sure that that is not going to be an issue. In this case, there is none, but we reviewed it and checked it. Lastly, for independence, we're going to look at the related IPLs. So for the scenarios we identified in the layer protection analysis, we also used a relief valve. We're going to list all of the components of that and make sure that there's nothing in common, or if it is in common, it's a low enough likelihood. Again, here, the person who did this identified potentially plugging as an issue, but it's considered a very, very low likelihood, so not going to be a concern. Important for this is that this related IPL section, this is not enough for that relief valve. You're going to need to document everything else that we've already gone through for that relief valve. So every single IPL gets its own IPL lifecycle requirements document, and they just reference each other. So make sure that you're doing that. This section is not enough to call that a full IPL. Next, we're going to look at the other lifecycle information. The first one is going to be revalidation plan. So this isn't a test plan, but how often are we going to actually check to make sure that this IPL is good? In this case, we're going to use the PHA cycle of 5 years. We're also going to include a list of alternate temporary protection. This is something that can be done if the IPL is not available for some reason. We're going to list it. This is not going to cover 100% of your cases. You're definitely going to end up with some where this doesn't work either. You can either list multiple under here or just make a change as needed. We really just want to catch most of the cases right here. Last section, we're going to talk about the effectiveness and auditability, which comes down to the individual components. We've determined that those components are looking at certain design conditions. We're going to list what design conditions we expect because that affects our probability of failure on demand of those components. So for each component and design condition, we're going to list that PFD, and here we're going to want to make sure that none of these numbers are higher than the overall PFD that we wanted for the system, which was a 0.1, so we're okay here. And the last thing we need to list here is the test frequency, because that heavily impacts our PFD. We're going to want to list that, and that way we can go back and revalidate how often this is tested. Sometimes that test is going to be common between all of them, so you're going to have the same test frequency. Sometimes it's more often for individual elements. It just depends on your IPL. So as you can imagine, this is a fair bit of documentation, but it's good to know that you have all the information you need to manage the life cycle. However, this works great for a small facility that maybe has a dozen IPLs or less. When you get to a refinery or a large chemical plant, you're going to start having a whole lot of documentation. You might have hundreds of IPLs, many hundreds potentially, and this becomes quite a bit of work. So how do you manage all of those IPLs? Well, you use the same information, but there's software available to help you. An example I'm going to be going through here is one called ARTS. And we're going to look at a facility that, a company that has multiple facilities across the country, and they're managing their IPL health through this software. So we can see that there's, of these 4 facilities, one in particular seems to be having a lot of trouble with their IPL health, Houston. So we're actually going to drill down to that, and now we're looking at just Houston. It's now split out by area or unit. And for the most part, they're actually doing pretty well, but Area B seems to be having some trouble with the life cycle of their IPLs. So we're going to drill down into that. And at this point, we're looking at the individual IPLs listed, all of the ones identified in the LOPA, and we're actually checking, have they been verified for independence, effectiveness, auditability? Are they included in your MOC? Are they included in the access security plan? You can see there's definitely some issues here. Let's drill down into IPL number 2 there. And here we get all of the same information that was on your safety lifecycle requirements document, and including the IPL description. We'd have sections for the independence, for the source, everything. Here in particular, we're going to look at the testing, and we're going to include all of the design conditions, PFD, and test interval. What's new on here is we're now going to tie into the test system and see what was the condition of that each particular component last time it was tested. And for the most part, we're good, but for example, the valve, the fuel gas valve, is in high vibration mode rather than low vibration. So that might affect the reliability. So we're going to flag that in a yellow. We don't know whether it's affecting it yet, but it could potentially. We're also going to look at when was the last test actually done. So if it's overdue, well, that's an issue. We're not meeting the specifications that we put out for this IPL when we created it. So that's actually a bit more of a severe issue. We're going to flag that in orange. And what we can do with something like this is look at all of our components of IPLs. We can get an entire list for the entire refinery or even the entire company and say which ones are meeting their requirements, which ones are not. Helps us prioritize fixing these so we know that we're going to be safe overall. Next is the recording of the IPL performance or reliability. This is pretty hard to do when you're using those lifecycle documents, except to only look back and say, based on our maintenance, when could we have relied on this IPL and when not. With a system like this, we can actually track, okay, right now there's a couple issues with testing, so we maybe cannot depend on this IPL fully, but it's most likely going to work. Or we could say that instrument was bypassed. This IPL would not have worked. That would be red in this case. So we want to look over time. In cases where it was green, excellent, or yellow, good, we were most likely able to rely on this IPL. So looking at this from a revalidation standpoint, we can say the last 3 years, 98% of the time, this IPL was probably going to work if we needed it. Given that we gave it a 90% reliability, we're in pretty good shape. However, we could do better. Now, if this, say, had only an 80% in the green or yellow over the past 3 years, we definitely could not have taken a 90% reliability or a PFD of 0.1 because we know it was not available for at least 20% of the time. So this helps you look at those situations and say, maybe we need something else in place of that particular IPL. Finally, we get to the managing change. As I said earlier, this is a pretty tough part of IPLs, especially when it comes to looking at the individual components. Now, if we've done the lifecycle document or we have software, we can actually create a list like this, which is all of your IPL components, initiating events components, and other IPLs. And we can actually search this to say, if we're making a change to any one of these, let's make sure it doesn't affect our independence, and we update our safety lifecycle requirements document. Again, that can be a lot of work when you have a lot of paper, but you can have software such as ARTS here where we can just search for the instrument we're changing, in this case, the pressure instrument that we know is in an IPL. And it'll output what IPLs it's used in, what initiating causes it's used in or are related to, and now we can actually dive into, with the change we're making, are we affecting this independence or effectiveness or really auditability of any IPLs? And we can look at the interdependence and make sure that it's not statistically significant for these particular, for this particular instrument that we're changing. So back to what I asked at the beginning of this section, what does all of this life cycle management really look like in practice? Well, there's certainly a lot of documentation you need to do to make sure that you know that you're independent, effective, and auditable. But that can either be a whole lot of paper or a system that you have in place, just like you would for your management of change, where you are actually managing it at a high level and looking at your IPLs holistically. So going back all the way to the beginning where I said, what is an IPL? Well, I hope you see now, an IPL is just a special safeguard that we can prove to be reliable through independence, effectiveness, and testing. And the way we actually prove that it's reliable is by documenting those 7 criteria that the Center for Chemical Process Safety gives us. If we manage all of those, we can prove that an IPL is reliable. But how do you actually document those 7 criteria? Well, there's many ways, including your existing systems or new software systems that are available that help you manage the full life cycle of IPL.
I'm sorry, we lost audio for a second. Hopefully we'll get it back. I am working on trying to get Patrick off mute. So please bear with us, Patrick. There you go.
Can you hear me?
Sorry, yes, we lost your audio for just about 30 seconds.
Okay, well, just really quickly, I'll go back over this, saying that the IPL is basically any safeguard we can prove to be reliable through the independence, effectiveness, and auditability. And we do that by documenting the 7 criteria provided to us by the CCPS. And we monitor that documentation and implementation of the IPLs through either software or documentation systems. So to these 2 incidents that I was talking about earlier in Buncefield, the Buncefield incident and the Texas City incident, Would they have been prevented if they'd had a proper IPL management system? It's obviously a little bit hard to tell because the past is the past, but at the very least, as these incidents occurred, the operators and maintenance personnel would have been aware that their IPLs were not working as required, and they would have been testing them more adequately, and hopefully we would have saved some lives. So thank you for joining us, and so you know, I've mentioned earlier that if you want a copy of the Lifecycle Requirements document, here's the 2 email addresses. You can email either of us, and we will get you a copy of that as an example. I'm going to turn this over back to Pam.
Okay, thanks, Patrick. We have a bunch of questions, and if anyone has any more, please use the chat box and send to host. First question, are alarms normally considered IPL? I didn't think so.
All right, that's a great question. Now, I've been using the term alarm throughout this. What I actually meant there was alarm with operator action. Alarm by itself is not an IPL. You need to be able to actually act on that IPL, so an operator needs to be able to act on it. In that case, they can be considered IPLs if you've documented that both the alarm and the action that the operator takes are independent and effective. And there's more information on that in even the purple LOPA book speaks to that a little bit more.
Okay, thank you. PFD of the safety system for a function is a sum of the PFDs of each of the subsystems. The slides seem to imply that PFD of the system for that function is simply the PFD of the worst component. Is that intended?
I was wondering if we would get a question there. That whoever that is obviously familiar with safety instrumented functions, where that's absolutely true. For most IPLs, we are taking that are not safety instrumented functions. We are taking we're making a lot of assumptions about the PFD, and they're very conservative. And while yes, it would be more accurate to get the actual PFD of the individual components and add them together, we can really make the approximation using the order of magnitude analysis that we're doing in a LOPA. We can make that approximation of adding them. There's more information on that, again, in the blue CCPS book. Really has a lot of information. Most important thing there is non-safety instrumented functions are treated a little bit differently when it comes to PFD than safety instrumented functions.
Okay, thank you. For this ongoing tracking over time, how does ARTS get the information for all the criteria, not only testing?
Well, most of this information is available in whatever sort of management systems you already have, whether that be your testing systems, your maintenance systems, or even your control systems. Really, the control systems are going to be the ones that are most important for the bypasses, which is usually where your IPLs really fail. But most of the information is available in various systems that you already have. You're actually probably even already recording the same stuff. ARTS just conglomerates all of that into one.
Okay, another question about the ARTS tracking software. Is this information entered manually by personnel, or some of it automatically entered from the PLC system?
Both. Depending on, I guess, to my last answer there, depending on what information you have, it can be automated, or sometimes it just takes some manual tracking. And what I've seen some people do is they do that as part of their process safety information revalidation ahead of the PHA. So they enter that information and look at it in hindsight, which is perfectly possible, and it's actually not too much work.
Okay, thank you. Could an alarm by itself be a safeguard, or is it for monitoring purposes?
I think that this is a bit of a repeat of that first
okay. Did we already ask that one?
Yes. Now, I guess there can also be alarms that are for monitoring purposes, where they're monitoring the status of an IPL. Those are sort of a unique case. They're really valuable in improving the overall probability of failure on demand. Again, from the blue book goes into a little bit more depth about that. There's all sorts of stuff about monitoring your IPLs with alarms.
Okay, thanks. Is your control system a safety PLC?
That is that's a bit tough to answer. I would say most of them are not. I cannot speak to industry as a whole. Generally, no, and the IEC 61511 standard makes the difference between a safety system or safety manager and a basic process control system. That's a pretty in-depth question, and definitely different depending on what facility you're at.
Okay, thank you. Is the alarm considered an IPL only if the action of the operator can be demonstrated? If yes, what is the nature of the demonstration? Only procedure or response needs to be timed?
Well, there's a few different ways to approach that. There's you don't necessarily need to prove the operator action of that particular IPL. What you need to do is basically manage your operations so that they're aware of what the IPLs are and what their actions are, and then you can perform a human reliability assessment on the operator to see what sort of reliability they get, and that can count as testing. You're testing a component, not the full loop, which isn't as good as if you can actually test the full loop from instrument to action. But I mean, we all live in a real world here. It's pretty hard to do that test. So let's see. The second part there was, do you need procedure or response need to be timed? Again, depending on what your human reliability assessment says on that, possibly, especially if you have a very limited amount of time to act. There are a number of papers, and I believe that the blue book also talks about how reliable people are depending on how long they have to act, and it's essentially a logarithmic function. If you have a lot of time, they're more likely to make the right choice. So if you're looking at IPLs where the operator response needs to be in minutes, as in less than 10, I would say you're going to want to test to make sure that they can actually do that. But longer, chances are the procedure is good enough.
Okay, thank you. Is an SIS function an IPL?
Yes, it is an independent protection layer, and normally we would include that documentation in everything we're saying. This presentation was focused on the non-safety instrumented functions because they're less well defined. Really, if you are managing a safety instrumented function, you're going to want to look to IEC 61511 for how to do that, not these CCPS books. Everything we've said here is based on 61511, but 61511 actually lays out, here's what you have to do, at least as much as a performance standard does. So the answer is yes, they are, but they are indeed managed a little bit differently than the other IPLs.
Okay, thank you. Is a BPCS and an IPL built in the same PLC?
I'm not quite sure what that is asking. So I don't think we've actually said what BPCS is. That's your basic process control system, which is whatever you're using to control your overall system that's not a safety manager. So that's defined in 61511. That's going to be your DCS or your PLC or whatever you're using for normal control. And IPLs will, most of your IPLs are going to be either in the BPCS or they're going to be completely separate, like mechanical relief valves. But just like the previous question there, safety and surrender functions are going to be in a separate system, a separate control system, and those are also IPLs, but they're defined a little bit differently.
Okay, thank you. For general purpose safeguards, for example, not scenario specific, such as a deluge system, how is the effectiveness criteria met?
Yeah, I think I had that listed as one of the ones that's a little more difficult to determine the effectiveness. The number one thing you're going to do is look at your industry codes and your company standards, the NFPA, et cetera. If you are meeting those requirements, I would at least hope that it's effective. As for how you test that, you would test against those codes. Whether that's a fully thorough effectiveness determination, well, that's hard to say, but at the very least, we know our codes are, our standards and codes are what we need to meet.
Okay, thank you. You say that you have to test the reliability of people involved in the IPL. How do you do that?
Your human reliability assessment, which uses all sorts of information like what they're being provided on the screens, along with how often they're trained and tested. You're going to want to look to that to determine how reliable your people are. Generally, though, if you just look at these two CCPS books, they have PFD numbers that you can use depending on how stressed or fatigued the personnel are and how often they take the action. You can use that as well if you don't want to go into depth, but really I would recommend a reliability assessment for your operators since you are depending on them.
Okay, thank you. How do you identify the PFD of individual components?
Well, sometimes if it comes down to the level of, for example, an input-output block, you can get that information from the manufacturer. But going back to, I think, one of the very first questions here, which was around adding up the PFDs versus just using the lowest, we use a lot of approximations, and to determine the PFD of the component, you can get industry data or look to the purple and blue books. They have some examples. So the example I gave in the presentation was where a relief valve depends on a check valve. Both of those have PFDs defined in those two books. When it comes down to CPUs and I/O cards, go to the manufacturer, but those are probably going to be common throughout your facility, so you shouldn't have too much work there.
Okay, thank you, Patrick. I'm sorry, but that's all the time we have for questions. So if you still have a question that you'd like answered, please send it to producer@aiche.org, and I'll send it on to Patrick. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Patrick Fisher for this very informative presentation. Thanks also to our participants for your cooperation and very thoughtful questions. Please visit aiche.org to replay this session or to view and sign up for our many others. A reminder to also please fill out the evaluation form that will appear on screen when you log out. Goodbye, and we hope to see you again in a webinar soon.